Donc, j'ai le plaisir tout de suite de donner la parole à Rodolphe Katra, donc, qui est au niveau de la recherche et du développement chez Medtronic, qui a la gentillesse de s'être levé très très tôt, parce que Rodolphe est aux États-Unis, donc avec le décalage horaire. Merci beaucoup, Rodolphe, de vous être mobilisé. Et donc, vous allez nous parler dans la suite de l'exposé de M. Alexandre, donc de l'intelligence artificielle pour une médecine personnalisée, ce qui est presque antinomique, entre guillemets, c'est les données massives pour aller affiner la thérapie pour un sujet donné. Donc, Rodolphe, je sais que vous allez faire votre exposé en anglais, même si vous êtes parfaitement francophone, mais que ce sera plus facile pour vous. Et je vous donne la parole.
Merci. Merci beaucoup. Bonjour, chers collègues. Je suis honoré d'être ici, même si c'est sur Zoom. Je regrette que mon français n'est pas tellement bien pour une rencontre scientifique, mais je vais donc le donner en anglais. Et j'espère pouvoir rendre justice à ce sujet-là. Alors, est-ce que vous voyez mon écran?
Oui, très bien, oui.
C'est bien. Alors, what is artificial intelligence? And everybody here probably knows that it's anywhere and everywhere around us. You cannot pick up a smartphone, you cannot look at a house tool without recognizing that there is some elements of artificial intelligence in it. But what is artificial intelligence? We use these words, machine learning, deep learning, artificial intelligence interchangeably, and to some extent they are. But to just define things and be on the same level, artificial intelligence is essentially a set of computer programs that are designed to mimic and replicate human intelligence and automate functions. Within artificial intelligence, there's a subset known as machine learning, and these are a set of algorithms that allow a program to learn from data without explicitly being programmed by an individual. And within that, there's deep learning, which is a newer field where the depth of the neural network allows you to do a lot more inference and recognizing patterns from within the data. These types of machine learning could be supervised, where the data that's put into the system is calibrated and annotated by expert physicians or practitioners in order to inform the model about the intent and the task that the operator was coding in it. Or it could be unsupervised, where the program learns by itself by distinguishing patterns from within the data, and that requires massive amounts of data. But regardless of the solution, the output ends up being a model that could be either locked, that means it doesn't change the moment you create it and you deploy it, it stays the same way forever. It could be adaptive, where it continuously learns from the data that it sees over time and adapts its behavior. Or it could be somewhere in between, where there could be a human in the loop that's interfacing with these AIs, controlling elements of it as it evolves. Now, there's many other variants of this, but this is the general application, the most common applications that we tend to see. So, what is machine learning in principle? And this is probably for a medical community and those who are not practitioners in machine learning technology, always ask that question. And the answer here is, well, it solves the same problem we've always had to face and we've always had to solve, but we do it in a modified approach. So traditionally, in the classic or digital signal processing world, a practitioner, usually an expert user, a scientist, a physician, or a mathematician, has to discover the hidden relationship between the data in a very causal and deterministic fashion and code these instructions into a program in a step-by-step fashion. And this way, the relationship between the input and the output has been completely described, but to some extent limited by the practitioner's understanding of the underlying problem. Machine learning, in contrast, tries to solve that same problem. However, it takes massive amounts of data and uses the final output, the annotation or the adjudication of an expert user, and without explicitly being programmed, tries to find the relationship between the input and the output in ways that sometimes even humans can't appreciate or understand, because it does this inference over massive amounts of data, way more than we practically do in any clinical trial to deploy medication or medical devices. Practically, what does that mean, and what does it do for the field of precision medicine, and how is it applied? Obviously, there's a spectrum. Machine learning and AI, which I use interchangeably, spans the field of, on the far end, the most benign, the most pedestrian would be automation of routine tasks, where it's used for clinical decision support. On the far extreme, it could be disruption that would be, that's emerging, and I'll talk a little bit more about that in the next few slides, where it could be a treatment recommendation system to guide therapy for patients as their conditions evolve. In the middle is where the bulk of the innovation is happening at this moment, where a lot of products and solutions that are machine learning based are being introduced. Everybody's heard of the Apple Watch that measures the ECG, or the algorithms that are being deployed for retinal diabetic retinopathy, or in echocardiography, and so on. These are algorithms that are paired with a device that allow you to create a new solution that historically has not been existent. So in the next few slides, I'll give an example of each one of these buckets. On automation, I will reference our focus on remote monitoring service, which is a service we provide to manage remotely patients that have implantable cardiac devices. This has become a very critical piece in our fight against COVID, where patients have to have their devices remotely managed, more and more so than prior times. In the new solutions area, I will discuss our newly introduced Link 2 that uses the first of its kind AI support as part of a device to monitor cardiac conditions and diagnose patients. And the area that excites me the most, the optimistic technologist in me gets excited about, excuse me, digital twin technology, where a complete virtual counterpart of any individual patient gets created in order to simulate the real condition, and it gives the physician and the practitioners an ability to try things without even interfacing with the patient. And once you find the optimal solution, then you can apply it to the patient as needed. This field has been very common in the area of aeronautics, where people use simulators to train pilots. It's been the same way in Formula One drivers, where they simulate the track and all the conditions are replicated to perfection. But in the field of medicine, this is new. And this is an area that we're going to hear more and more about it over time. So let's start with the automation. Most of you are probably familiar with our ICM technology. This is our implantable cardiac monitors that are used to diagnose conditions like syncope, stroke, AF, and other symptomatic cardiac episodes. The data from these devices tends to be enormous. As mentioned in my previous speaker, a physician handling such patients will be inundated by a massive amount of data that they need to go through to deliver the best care possible to the patient. And this was done by design. These devices are designed to be extremely sensitive and rather less specific, because you don't want to err on missing an episode that could have been detected in the patient. So they're designed to be more sensitive. The problem with that is now you end up with way more data that in some cases is not important or clinically relevant. Data coming from these devices goes through a monitoring center, through either a bedside monitor or an app, where we have 2 certified cardiac technologists that read every transmission coming in. They annotate the underlying arrhythmia and then score those transmission through a red, yellow, green priority system, and then notify the physician based on the criteria that they've wanted to be alerted on. As you can imagine, this is a very labor-intensive process that is not necessarily scalable, especially when you do 2 human reviewers to quality control the interpretation. So you're always getting a second opinion on every interpretation. So for this area, we developed a machine learning. Actually, it's a deep learning algorithm that's trained on over 1 million episodes. And our thought that we could replace one of the human interpretations with an artificial intelligence solution. And the way this works is all the transmissions that come in will be shown to an AI engine and a reviewer in a blinded fashion. So they don't know what every other person is doing or every arm of this flowchart is doing. It goes into a decision engine where if the AI and the reviewer agree to the same annotation, then the results are automatically finalized in a report. If they do not agree, or if there is a divergence of opinion, a secondary human reviewer is brought in to arbitrate between who was correct and who was incorrect. Now, this is one implementation as a decision support tool, but you can imagine that as we get higher regulatory approvals and get to prove the clinical performance of these algorithms, we can start using them without a human in the loop. We can start using them where if you have an extremely high confidence of the AI performance, the data can go into finalization automatically. But if it requires any human review because the confidence of the AI is not very high, it can go into the flowchart where it gets reviewed by a human and in a blinded fashion. And if there's agreement with what the AI had determined, you can go into finalization and the flowchart continues. So this is a solution where machine learning is applied to create automated processes for remote patient monitoring. It uses two nested deep learning algorithms that process not only the arrhythmia itself, but also a rate-based model to allow for explainable interpretation of the signal to a physician. And it's able to achieve over 88% reduction of burden for the secondary reviewer. Moving on to the next case, this is an example of our link to Accurhythm AI with our machine learning solution. This is the same situation where you have an implantable cardiac monitor transmitting the data to the cloud. You have two machine learning algorithms in the cloud that process false episodes of pause and AF, thereby reducing the burden of looking at all these episodes if they are not true episodes. Comparing it to previous generations and looking at its final performance, you're able to maintain over 99% sensitivity. So you're not missing any true episodes that are occurring, but you're able to reduce by 97% the pause episodes and 74% the atrial fibrillation episodes that are false. This is the first machine learning introduction to an ICM implanted device in the world. This is going to allow complete elimination of false positive episodes from clinical burden, eliminating the need for additional staffing and resources at the clinic. It delivers the most optimized burden reduction while maintaining patient diagnostic yield. And it's done in a distributed computing model where now for the first time we use algorithms partially in the CAN, in the implanted device, and partially in the cloud as a system that works together appropriately. The last bucket around the digital twin, this is an area of extreme excitement, but it's still nascent, it's still new. And since we're talking about precision medicine for the future, how do we move from general applicability of machine learning algorithms to personalized and customized care of patients for the uniqueness of their condition and how they interface with their healthcare system? This is an example, and it's this in its simplest form. You can imagine it or think about it as a simulation where a complete digital replica of a given patient is created from population level data, taking into account all the clinical trial knowledge, all the guidelines knowledge, all the published literature, along with all the unique mobile data, omic data, EMR, healthcare data, combined with imaging and all interventions into one model. It could be a statistical or mechanical deterministic model. And then when you get data from an individual patient, you leverage the totality of all the population level knowledge that you have to create a completely personalized and customized experience for managing care. This solution, while it's still nascent, is the future to democratize and bring access to the highest level of care, even in the most rural and remote areas of the world, where you may not have access to the best trained physicians and the best available solutions in the world. Well, this is the practical piece of it, but when in reality, the deployment of machine learning algorithms is always fraught with barriers for adoption. Clinical performance is always going to be a must. Regulations and access is always a limiting factor. We know reimbursement always plays a role in limiting who gets care in what areas, as well as mentioned earlier, data and patient privacy of that information. Explainability is key because a lot of the physicians want to understand why and how the machine learning algorithm is making the determination that it does. Moving into personalizing solutions versus the way we're used to thinking in a clinical trial where we do cohort-based analysis with statistical separation of control group from an intervention group. This is a very different space where you're thinking of an N of 1 for an interpretation, and data bias, obviously, within the nested data sets that are used for training these models. But as with any technology, there's a Rogers innovation curve and adoption curve where there will be early adopters, there will be innovators that will probe the limits of what AI can and cannot do. Ultimately, we will have some diffuse adoption, and there'll be those who will never believe and never want to use such technology because of various reasons. As mentioned by Alexander earlier, it may be against what they want to practice and follow. So here is my ending about as in optimism, but as a practical futurist. AI and machine learning is going to follow the same Gartner hype cycle as every other modern technology. Right now, we believe it will do everything for everybody under any condition, anywhere. Just sprinkle some AI, poof, voila, everything gets solved. We're going to get through some disillusionment and disappointment with this technology, but ultimately get to a level where we're going to get a steady state benefit for the healthcare system as we learn how to deal with this technology over time. This is true for AI. This has been true for every other technology, including 5G, including the introduction of the internet and everything else before that. But as we move towards precision medicine and what is known as healthcare 5.0, I will draw the contrast to the revolutionary phases of the industrial system, where we moved from mechanization, electrification, and automation in phases, leading to where we are now, which is total digitalization and using at a higher level data analytics and AI to automate processes. The future of precision medicine and the optimism in me says that we're going to be in a world of personalization in the future, where every person is treated uniquely with algorithms that adapt to their unique conditions. And this way, everybody gets the most out of the healthcare system in the best of ways. With this note, I thank you for your attention. And again, I apologize for running quickly. And I'll take any questions you may have.
Merci beaucoup, Rodolphe, pour ce très bel exposé sur l'intelligence artificielle et la médecine personnalisée. Alors, j'aurais deux petites questions pour vous, et un petit peu dans la suite de ce que nous disait tout à l'heure Laurent-Alexandre, et puis le complotisme et l'obscurantisme, finalement, parce que pendant des années, en santé, en médecine, on a essayé d'expliquer, de comprendre, de valider. Et puis maintenant, on a des outils, et je pense notamment au machine learning, qui nous disent « c'est comme ça », mais qui ne nous disent pas pourquoi. Donc comment on va convaincre, entre guillemets, la communauté médicale et convaincre, je dirais, les sceptiques, hein, que c'est comme ça qu'il faut avancer demain. C'était mon premier commentaire. Et puis, j'avais aussi un deuxième commentaire sur le digital twin, le jumeau numérique. Ça vous effraie pas que demain, on ait chacun notre jumeau numérique?
Thank you for these questions. So let me address l'explainability component d'abord. This is something that is very important to the medical adoption, and it is something that is currently being worked on significantly. There's a lot of tools and solutions that are being created to translate the black box machine learning solutions to the current decision-making process in medicine. So I'm going to take the example of anarrhythmia detection. The physician is used to seeing the 12 lead, they think in the time domain, they see the QRSs, they look for beats per minute, they look for RR interval. These are traditional ways of thinking about the ECG to diagnose a certain arrhythmia, looking at morphology as well. So what is being done now is there are tools called explainability tools, and there's a few of them out there where they're taking the machine learning output and translating it to the way of interpretation that current physicians are doing. In many cases, we're able to reach a near analogous interpretation where you can translate the findings of the AI in ways where the physician could be pointed to where in the ECG the problem is occurring and why the AI reached the decision that it did. This is still a growing area. It's being done in imaging. It's being done in time series analysis, like in ECG interpretation. But I have to admit, there will be cases where it will be very difficult to interpret these solutions. And I give an example of something Mayo Clinic has published on recently. They were able to see from the ECG, the machine learning algorithm was able to determine the gender, the age, and the ethnicity of a patient just looking at the ECG. I am not sure any explainability could be used in that sense to explain to a physician that just looking at the QRS, you're able to tell that a person is a female, 70 years old, and African American. But that doesn't diminish the strength of the finding. That doesn't diminish the accuracy of the result. It's just a way we need to get comfortable accepting that we won't understand the language spoken by machine learning algorithms, and provided some elements of it are explained and it's perfectly validated and approved, that there has to be some face value acceptance of if it's properly validated, of course, and regulatory cleared for that application. I don't know if that's an acceptable answer for many people, but this is the reality of it, I'm afraid to say. The second question around the digital twin, this is currently being done right now. A lot of these algorithms that adapt to your own breathing patterns in the Apple Watch or sleep patterns and so on. It exists on a small isolated scale where we can collect data on a personalized level, but we end up with guidelines that are on a population level. So what's happening now with the digital twin is there's a field where you're taking all of these personalized level data that sits with a lot of these smart devices, a lot of these personalized tests, and you create a counterpart to it by applying the specific branches of the guidelines that match that patient's application. So in these instances, we know of conditions where you do a CT for a patient and you take the actual morphology of the patient's heart and you overlay on it with a VR or an AR technology, unique surgical procedures for that individual patient. So it's being done to some extent now, but we're not using it so much for simulation of what would happen if I change the medication for this patient without really changing the medication. So running a simulation around, do I switch medication? Do I change dose? Do I change timing of the medical regimen? And would that give better results for this individual patient if they're, let's say, a fast metabolizer of medicine or a slow metabolizer of certain medicines? These are all questions that we're starting to work on. And there are many companies that are created now that all they're doing is digitizing the medical literature that over the last 100 years and creating these new digital twin models that are going to evolve over time.
Merci beaucoup. C'est tout à fait passionnant et on voit que vous êtes vraiment passionné par le sujet. On va devoir par contre avancer dans le programme. Encore une fois, merci.